Greetings and salutations, magical chemists. Let's talk about the glorious and pesky particles known as electrons. Electron orbitals, of course, are the three-dimensional regions around the nucleus that indicate the probable location of the electron. Each individual orbital is located at a specific main energy level and a sublevel. The main energy levels, which are sometimes referred to as shells, are referred to with the letter N. This is also the principal quantum number. And it tells you the general amount of energy and the distance from the nucleus that a given electron in an orbital possesses. Each period or row on the periodic table indicates the main energy level. Now, energy sublevels, which are sometimes called subshells, are referred to by L, the angular momentum quantum number. And this tells you the different shapes of the orbitals that exist within the same main energy level. Unlike the main energy levels, which we refer to by numbers, the sublevels are referred to by letters. It is important to note that a maximum of 2 and only 2 electrons can fit in a single orbital. So you may recall that we represent a single orbital, usually just with a line. So the 2 electrons fitting inside, one would be spin up and one would be spin down. Now, usually we represent electrons with arrows, but it takes a lot more energy to write full arrows, so most of the time I'll be using the shortcut where you do half arrows. Now, electron configuration is something that's really useful because it basically tells you the exact level and sublevel of every single electron in a given atom or ion. Now let's go ahead and take a look at each of these specific energy sublevels, which you may or may not recall. So they are referred to by letters, lowercase letters, which is kind of hard to show when you're not writing something, but it is, of course, S, P, D, and F sublevels. So the shapes of these can be remembered by using the letter. The S looks pretty much like a sphere. P looks like a peanut. The D look mostly like a daisy. It gets kind of weird, though. And the F orbitals, well, the F orbitals are just too freaking complicated to really have an exact picture. Each different sublevel has a different number of orbitals within that sublevel. S orbitals, or S sublevels, are the smallest. They fit a single orbital, which means only 2 electrons can fit in an S sublevel. The P sublevel is a little bigger. It can fit 3 orbitals, which means it can fit a maximum of 6 electrons at a given P sublevel. So the pattern continues. D can fit 5, and F can fit 7, which means that a D sublevel can fit a maximum of 10 electrons, and an F sublevel can fit a maximum of 14 electrons. Luckily, there's a quick trick to make sure you never forget the orders of your sublevels, S, P, D, and F. It's because splendid people don't forget. What don't they forget? Well, the order of their energy sublevels, of course. Okay, let's take a moment to take a look at what these orbitals actually look like. So the S orbitals, just like promised, indeed are spheres. And the P orbitals, they do kind of look like peanuts. They're peanuts, though, that have a node in the middle, so there's no actual electron density at the very center between them. But, kind of like a peanut. And then the D orbitals, now most of them do kind of look like daisies with just 4 flower petals, but there's this one really wacky D orbital at the end that, well, there's a lot of math that you can use to figure these out. Luckily, we don't have to worry about that. We just get to admire their awesome shapes. Speaking of awesome shapes, those F orbitals. Be like, what the F? F orbitals, that is. Well, they are just a little teensy bit of crazy, but they have all sorts of a variety of interesting shapes. So let's look at the periodic table and remind ourselves how you can use the periodic table to derive all the information about these energy levels and sublevels. It's beautiful. You may recall that we refer to different locations on the periodic table as blocks that are referenced by the sublevel that their outermost valence electrons are found in. So the first 2 groups on the periodic table are called the S block. Now each energy level, or each row, is our principal quantum number or main energy level. So notice you have 1s, 2s, 3s, all the way down. So as long as you know the rho, or the energy level, you'll always know which s orbital you are talking about, because they are always found at that energy level. Okay, so after S, so you fill in the first energy level and you get S. Oh, one more thing to realize, your S block, it includes helium. Poor helium. Remember that hydrogen and helium are so tiny, their electrons are only on the first energy level. And the first energy level, which is really close to the nucleus, is so tiny it only fits an S sublevel. So technically helium is still part of the S block, but it's a noble gas, so we stuffed it on the other side. But after the first energy level, we hit the second energy level. There is the S block, and then there is the P block. The P block is also determined by what energy level, so 2P is on the second energy level, 3P is on the third energy level. Notice this is where, in your P sublevel, you don't have to memorize that a P sublevel fits 6 electrons, because you can just look at the periodic table and count the P block. Not awkward at all. Well, if you count all the way from boron to neon, it can fit exactly 6 electrons. And you could do the same thing with the S block. The S block, of course, only fits 2 electrons. Then, if you go far enough down, you will find the D block, your transition metals. You may recall that the D block's a little bit weird, because the D sublevel starts to exist on the third energy level, but it's not really kicking in on the periodic table until the 4th row, and it has to do with overlap between the orbitals as they get closer and closer together. But the trick to remember is that whenever you hit the D block, it's always going to be n-1. So you find the row you're at, subtract 1. So that's why if I'm on the 4th row, I must be at 3D. Last but not least, we of course have the F block. The F block is the block that is so large it fits 14 stinking electrons that you can't even fit it in with the rest of the periodic table, because it would make it basically too big to fit on a piece of paper. So we've taken the F block and we've moved it to the bottom. Now, because of all the overlap, even though the F sublevel starts to occur at the 4th energy level, so 4F is the first time you'll see it, it doesn't actually show up until the 6th row of the periodic table. Notice where this is coming from. So that's why if you're looking at the F block, and honestly we very rarely do, very sadly, I know, it is always going to be n-2 when you are looking at it. So look at all that delicious information you can get just from the periodic table alone. Let's look a little bit more at that overlap we were talking about. So the thing that is very important to recognize, so energy level 1, n equals 1, this is closest to the nucleus and thus the lowest energy. It's like the ground floor if you're in a building. Notice that there's a pretty big gap between the first energy level and the second energy level. But as you get further and further from the nucleus, the energy levels are getting closer and closer together. And that's why the sublevels start to overlap. So for S, the lowest energy sublevel is lower in energy than 3D, even though 3, just as a main energy level, is technically lower than 4, and things start to get a little messy. But as long as you follow the periodic table, you will totally be okay. Now, it is technically possible for electrons to move between different energy levels. And the only way to do that is by either gaining or releasing energy. So electronic transitions occur if you absorb energy, that electron has enough energy to jump up to a higher energy level. But during emission or release of energy, an electron is dropping down to a lower energy level. How much energy? Well, that really depends on how big of a distance it's jumping up or falling down. It's basically the difference between the energy levels it's transitioning between. So notice, okay, so these are classic questions. They're like, okay, you can have emission and absorption. So if the electron is transitioning from n equals 1 to n equals 4, first, that means it's going up. So does that mean it is emitting or absorbing energy? Hopefully you recognize it's got to be absorbing energy. But the question is, wait, which one? Is it the red light or the UV light? Well, this is where you might need to remember back in the day, but UV light is at a higher energy than red light. So I would like you to totally go ahead and try these problems and see what you think. And then when you're ready to check your answer, unpause the video. Well, the only way to answer this is to notice the difference between the energy levels. If you're jumping up from energy level 1 all the way up to energy level 4, that's a really big difference. But if you're just jumping up from 4 to 5, that's going to be a much smaller jump and require less energy. So for the absorption, the lower energy absorption, that's going to be the red light absorption occurs when you have the tiny jump up. But the higher energy absorption is when you have the giant jump upward. So that gives us our different absorptions. So that means the emission must mean the dropping. But now it's going to be, so similar idea. If you have a huge drop, you're going to release a lot of energy. But if you have a small drop, you're only going to release a small amount of energy. So that's how you would figure out a question like that. Okay, now let's start talking about how we actually fill up electrons into our orbitals and determine electron configuration. Well, there are certain rules we use. So the Heisenberg uncertainty principle says you cannot determine both the position and the velocity of an electron or any other particle, but we can still figure out its probable location using these 3 rules. The first one is the Aufbau principle. Aufbau is German for building up. And now it's talking about electrons in the ground state, which means they're in their lowest energy state. They're going to go into the lowest energy orbital that's open. It's just like it's called building up because if you're going to build a multi-story building, you can't start building the 7th floor first. It will crash to the ground and become either your first floor or rubble. You have to start on the first floor. Same with electrons. So if you want the try to draw the orbital diagram for hydrogen, well, the lowest energy level is 1, closest to the nucleus. Lowest energy sublevel is S. So that electron, the 1 electron for hydrogen, has to go into 1s. Not 2s or 2p or 7s or anything other than 1s if it's in its ground state. Okay, Pauli exclusion principle, that's a fun one. It says no 2 electrons can fit in the same orbital with the same spin. Basically, they can't both be spin up or they can't both be spin down. So if you look at helium, of course has 2 electrons. According to the Aufbau principle, they're going to go into 1s, lowest energy available. But then, okay, well the first electron, by convention, we say that the first electron is always spin up. That means the second electron is going to be spin down because they cannot be in the same orbital with the same spin. Now, the Pauli exclusion principle also talks about quantum numbers. The more efficient way of saying it is saying no single electron can have the same set of 4 quantum numbers. They all have to have at least one quantum number that's different. Luckily, or unluckily, because I love quantum numbers, but quantum numbers are not AP tested. So if that was one of the things you're like, oh my God, I never got quantum numbers, you are safe. We are not going to go over them because they're not going to show up on the AP test. All right, one more rule, Hund's rule. This is sometimes known as the good parent rule. It used to be called the good mother rule, but that's very genderist, and frankly, anyone can be a good parent. Well, the good parent rule, Hund's rule, says that, okay, if you're a good parent and you have 3 children, and you've got a plate of cookies, you're going to give each child 1 cookie before any child gets a second cookie. That's only fair. Well, Hund's rule says same thing is true for electrons. Now, this only applies to what we call degenerate orbitals. That just means orbitals that are found at the same energy level and sublevel. Like, for instance, 2p would have 3 orbitals. So let's go ahead and take a look at nitrogen. Nitrogen has 7 electrons. So the first 2 electrons go in the 1s orbital, and then that's full, can't put any more, so the second 2 go in the 2s orbital. But wait, I still have 3 left. Well, in my 2p sublevel, since I have 3 electrons left, I get 1 electron in each orbital. Only if I add another one would they all start doubling up. Oh, I forgot to fill in the stuff about spin. I already kind of talked about it. So the idea is spin up. Now, spin is not actually spinning, but it works as a macroscopic understanding of a quantum mechanical principle that frankly makes no sense. So we represent spin up either with an up arrow, or if you are lazy or efficient like me, half an arrow. Similarly, spin down, down arrow, or more efficiently, the half arrow. All right, let's try some practice problems. So there are 4 different orbital diagrams shown below. I want to know, for each example, what does it violate? The Pauli exclusion principle, the Aufbau principle, Hund's rule, or none of the above? So go ahead and try it, and when you are ready to check the answers, well, you know what to do. Unpause the video. Okay, well that first one should look epically wrong to you. It's violating the Pauli exclusion principle because you can't have two electrons in the same orbital with the same spin. Plus, it doesn't fit 3 electrons, but that's a whole nother problem. All right, on the second one, because you have an electron that is jumped up, it's an excited electron. Well, according to the Aufbau principle, if you are at the lowest energy state, that electron should be back over here. So it's not in the lowest energy orbital available, so it's violating the Aufbau principle. For the third example, that one's good to go. It doesn't violate anything. Which means, last but not least, I bet you can guess, this is a violation of Hund's rule. They are not being a good parent and sharing their electrons. All right, now that you know the rules, let's talk about electron configurations. There are 3 main types of electron configurations that are utilized. Orbital notation, or an orbital diagram, is the one we were using on the previous page. It's where you literally draw every single electron and every single orbital. In this picture, it's shown with boxes, but we usually just use lines because nobody's got time to draw boxes. Luckily, there is a shorter way, so you don't actually have to draw the electrons. In the electron configuration, the standard or complete electron configuration, instead of drawing out the orbitals, you just say which energy level and sublevel that the electrons are found in, and then you use a superscript to tell you how many electrons are found there. So this isn't like 1s squared. No, it's read as 1s2, 2s2, 2p3. It just means in the 1s energy level and sublevel, there are 2 electrons. The 2s energy level and sublevel, 2 electrons, and the 2p energy level and sublevel, there are 3 electrons. Yay for superscripts. Now, that can still take a while, especially if you start going further and further down in the periodic table. So there is an amazing and beautiful thing called a noble gas electron configuration. This is my favorite because it's the shortest. Chemists recognized that, according to the Aufbau principle, the beginning of your electron configuration is always going to be the same. 1s2, 2s2, 2p6, 3s2, 3p6, yada, 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 until you end. So the only thing that's actually different is the ending. So what they said was, let's just go ahead and abbreviate all that beginning stuff, because it's not going to change, and we're going to abbreviate it with a noble gas. Please notice that we put the noble gas in square brackets. The only thing that's sneaky about the noble gas configuration is figuring out which noble gas to use. But you just use the periodic table, of course. So for nitrogen, notice that nitrogen is at energy level 2, which means we can't use neon because nitrogen doesn't go all the way up to 10 electrons. But we can use helium. So to find the noble gas, you find basically, it's like you go to the end of the row to find that, and you go up by 1. So that's how you find, because that's the only one that represents the filled energy levels. Of course, that means for nitrogen, it's not a very good abbreviation because helium's really small. But as we have bigger and bigger and bigger atoms, the noble gas configuration is the way to go. So when you are writing your electron configurations of whatever variety, all you have to do is follow the periodic table to determine the order in which electrons fill elements. You just start from the very beginning, because Aufbau principle, you always start with 1s, and you go across the periodic table and fill it in until you get to the end. When you get to the end of that row, if you still have more electrons, you go and you start at the beginning of the next. And if you get to the end of that row, you go to the beginning of the next, and so on and so forth. Because electrons are always going to fill in the exact same order. And you don't have to memorize it. Please, for the love of chemistry, don't memorize that. Just use your periodic table. Now, there was one sneaky thing that we don't usually tell you about in pre-AP, but in AP, of course we do. It's what happens when you remove electrons. And it's only going to be a problem with D-block elements, your transition metals. It turns out when you are removing electrons from a transition metal, you have to remove valence s electrons first. It has to do with weird energy considerations, but you don't have to know why. You just have to remember that it's a thing. So notice, neutral iron. We find iron on the periodic table. Well, it goes all the way up to the 4th row, so it fills in 4s, and then it's got 6 3d electrons. So you can actually do a noble gas orbital diagram. Notice I'm just abbreviating all the earlier filled rows with argon, and then I'm just looking at 4s and 3d. Well, that's great. I've got my 4s2 and my 3d6. But when it forms an ion, so let's see Fe2+, notice, it's the 4s electrons that get stolen first. It's just a thing that happens. And then, only then if you lose, because of course you can have iron 2+, but you can also have iron 3+. Well, after it loses those 4s electrons, then and only then do you start stealing electrons from the 3d sublevel. So just watch out for those pesky transition metals. Okay, one last thing, and then we will be full up with tasty electrons. You may remember the term isoelectronic from pre-AP. Iso is a prefix that just means same. So things that are isoelectronic have the same number of electrons. One of the things we do in AP is a lot of the times we're not just looking at neutral elements, we're looking at ions. So we want the electron configuration for S2-. Well, S2- of course means sulfur that has gained 2 more electrons. So it is going to end, we are going to end with the 3p, because we're on the 3rd energy level, but instead of being 3p4 like normal, it's going to end with 3p6. Well, I bet you already realized when we were looking at the periodic table, that is exactly isoelectronic, same number of electrons, 18, as argon. So the very last thing you're going to do before you're free is you are going to identify a couple of atoms or ions that are isoelectronic to S2-, other of course, than argon. So take a moment, use your periodic table, and try that. When you're ready to check, unpause the video. Well, if you want to find things that are isoelectronic, you better count electrons. Notice that chlorine has 17, but chloride adds 1, goes to 18. So chloride is totally isoelectronic. But also, hey look, potassium has 19, but if it loses 1, then it'll be isoelectronic. Calcium needs to lose 2 electrons to get down to 18 and be isoelectronic. So the chloride ion or a potassium ion with a positive charge, calcium with a 2+ charge, all of those are ions that are isoelectronic to argon and the sulfide ion. All right, you do not need to do the bottom of this page. We're going to work on this in class. Go electrons, go! I'll see you there.